In a previous video, we determined that a penny thrown from the roof of the Empire State Building would certainly not kill anyone below on the street. But what if we changed some factors of this problem? Could we get the falling penny to become more dangerous, even lethal? For example, what if our penny was denser? What if the penny fell on its edge instead of tumbling? What if it was falling in a vacuum? These are some of the variations viewers wondered about from our first video, so let's do some math, see what we come up with. Welcome back to Math the World. If you haven't already watched part 1 of this video series, go check it out. The link is in the description below. We'll be using the models we developed in that video for this video today. And in part 3 of this series, we'll mathematically throw a bunch of objects off the Empire State Building to see what objects could actually kill someone below, so make sure to comment what objects you'd like us to throw off the Empire State Building. Virtually, of course. In order to determine if a penny could kill someone, we calculated its average and peak impact force, and compared it to the impact force of some situations where we know people have died from blunt objects hitting them in the head. We explored both a boxing scenario and a baseball scenario and determined that around 3,700 to 5,500 newtons is needed for a fatality. Our penny, on the other hand, only generated about 74 newtons at its peak, only enough to really feel like a flick to the head. But what if our penny had more mass? What would its mass have to be to become lethal? This is a pretty simple exploration. We can take our formula for impact force that we used before. We need mass, velocity, and contact time. The velocity and contact time will stay the same, and we can replace our mass with a variable, say x, and solve for x. We can see this visually in this graph as the intersection of our impact force graph with the line 3,700. We see that if our penny had a mass of 0.252 kilograms, or about half a pound, it could become lethal, generating 3,700 newtons of average impact force. That's quite a lot more mass though, 100 times more actually. Unfortunately, there's no material found on Earth that we could make our penny out of to achieve that mass without changing its size as well. We'd need a material 100 times more dense than zinc, the main element pennies are made of nowadays, but the densest element on Earth is osmium, which is only 3 times more dense than zinc. But a low-mass black hole, like GRO J171924, would do it. Its density is estimated around 735 grams per centimeter cubed. But there might be a lot more to worry about than blunt force impact if a penny-sized black hole was coming at you. What if instead of changing mass, we could change velocity? Our tumbling penny generated 74 newtons of peak impact force. How much force would the penny generate if it didn't tumble while it fell? What if it fell on its edge all the way down? Having the penny fall on its edge will change our penny's velocity, but the mass and contact time will stay the same. We used this equation to calculate the penny's terminal velocity. We needed mass, gravity, air density, cross-sectional area, and drag coefficient. For this new scenario, everything will be the same except cross-sectional area and drag coefficient, since we're changing the orientation of the falling penny. We found both the area of the penny's face and edge and averaged them to estimate the cross-sectional area as the penny tumbles. Let's replace this value with the area of just the edge of the penny to see what we get. We also used the drag coefficient of a flat circular disc, but this new shape would be a thin vertical cylinder. It was challenging finding existing data on what this drag coefficient would be, but by extending this existing model using a line of best fit, we'll estimate the drag coefficient as 0.4. Plugging these in with all our other values gets us a terminal velocity of about 71 meters per second, which is about 158 miles per hour. Pretty fast, actually. Now we can plug that into our impact force equation, and we can get 177.5 newtons of average impact force and a peak of 355 newtons. Neither the average nor the peak are in the range we determined was needed for death. It might leave you with a small goose egg, but not much else. So falling on its edge still isn't quite enough for death. What if our penny was falling in a vacuum? Without air resistance, it could reach even greater speeds. Without air resistance, our velocity equation becomes much simpler. Velocity is the square root of the initial velocity squared, which is 0 in this case, plus 2 times gravity times displacement. Gravity is 9.8 meters per second squared, and displacement is the height of our penny that's being dropped from, so 381 meters. That gives us a velocity of 86 meters per second, which is almost 200 miles an hour. Pretty dang fast. To get the impact force, we multiply that by its mass, divide by contact time to get 215 newtons on average, and 430 newtons at its peak. Still not enough to kill you with blunt force. Even if a person threw the penny down, so it had an initial velocity of 50 miles an hour, it would only achieve a speed of 89 meters per second and increase the average blunt force to 222.5 newtons. Still not enough to kill someone. Okay, so a penny-sized black hole would kill you if dropped from the roof of the Empire State Building. But a normal penny, falling in a vacuum, won't quite do the trick. What if we dropped it from a greater height inside our vacuum? How high would the penny need to be to kill you? And how fast would the penny need to be going? These are in essence the same questions, since in a vacuum, displacement and velocity are proportional. So far we've been using two formulas to determine lethality, impact force and velocity. We'll need to compose these two functions into one function and then solve for 3,700 newtons, the lower bound of our deadly force range. By placing our velocity equation inside our impact force equation, we get this function here. By setting it equal to 3,700 and solving for x, we get a height of over 100,000 meters. That's over 12 times higher than Mount Everest. At this distance, the penny would be traveling 1,480 meters per second, which is 3,310 miles per hour. To be honest, at this speed, there are many other considerations besides blunt impact force. In fact, our penny probably isn't even considered blunt anymore. It's essentially a bullet. You'll be dying of a lot more than blunt head force trauma. On that happy note, thank you for watching. If you haven't already, hit subscribe and leave a comment below for what objects you'd like to see us mathematically throw off the Empire State Building in part 3 of this series. See you next week on Math the World.